The next talk is by Amiel Sternberg. It's a very general title. It's Molecules and Radiation.
Yes, okay. Thank you very much. It's a real pleasure and an honor to be here for this great celebration. I want to thank Kate, Jim, and Hossein for organizing this meeting. We're all part of the Dalgarno family, and I'm proud to be a member of this family, and it's just been great to see everybody. I'm going to talk about molecules and radiation from star-forming regions to quasars. As Pat just said, this is a very broad subject, and I can only touch on a few concepts and topics, and along the way mention my scientific relationship with Alex, which has spanned, shockingly enough, decades now. Now, a lot of astronomy has been thrown out to the non-astronomers here. I thought I'd just spend 30 seconds or so just sort of putting things into a little bit of perspective. We live in a spiral galaxy called the Milky Way, consisting of 100 billion stars or so, spread out in a thin disk with a diameter of about 100,000 light years. The disk is thin, of order 100 to a few hundred light years. It consists of spiral arms in which stars are forming to this day. And another important feature of our galaxy that's important for something I'll touch on later on in my talk is that it contains in its center, we now know, a 4 million solar mass supermassive black hole. We now know that all galaxies contain supermassive black holes in their nuclei. In fact, in the current picture of galaxy formation, the formation of supermassive black holes and galaxies are intimately related. The interstellar medium is a complex, dynamic entity. It's not in equilibrium, far from equilibrium, as Tom indicated. It's highly inhomogeneous. A simple number to remember is 1, which is the average density per cc, hydrogen particle density per cc. But it's highly inhomogeneous, consisting of multi-phase media ranging from hot ionized gas of hundreds of thousands of degrees, dilute ionized plasma, down to dense cold clouds, including the molecular clouds, the cold molecular clouds. The interstellar gas is exposed to starlight, shock waves, energetic particles, cosmic rays, magnetic fields, and the ISM, as I said, is dynamic. It's heated and energized by stars. The energy is transferred from the stars to the medium by outflows, radiation, supernova explosions. Another number to remember is that the total galactic ISM mass is about 5 times 10 to the 9 solar masses. 95% of the mass is in the cold phase, and about 95% of the volume is in the hot phase, hot ionized phase. Another important fact that we've now known for decades now, so really from the 1970s, is the fact that stars form. The formation of stars occurs in cold molecular clouds. The formation of molecular clouds is a precondition for the formation of stars. And as I said already, in our galaxy, star formation is something which is occurring even today. The global star formation rate in the galaxy at the present time is about 5 solar masses per year. Well, here's a beautiful picture of a star-forming cloud, the Eagle Nebula. It's a fantastic picture, courtesy of the Hubble Space Telescope. When these sorts of dark clouds were first discovered in previous centuries, actually, they were rather shocking. It's a quote from Sir William Herschel, who was German, of course. When he first saw one of these on the sky, he shouted to his sister, who was also an astronomer, "Mein Gott, da ist ein Loch im Himmel." He was actually, so translated, "My God, there's a hole in the sky." He was quite frightened by this. So you see this fantastic picture, 10 light years across. Well, this is a star-forming cloud according to God. But it's also interesting to think about star-forming clouds according to Alex. And here I really want to make a point that, you look at this incredible complexity, and one's initial response is to almost give up. I mean, how can one ever understand the phenomena that one's looking at? So incredible complexity. And one of the great contributions of Alex, and I think Bill Klumperer mentioned this in his opening remarks, is just this very rational approach to sort of just dealing with the complexity, but step by step, trying to understand the microphysics in a very detailed way. And so star-forming clouds, according to Alex, consist of models which are usually not always steady-state, one-dimensional models with radiative transfer, but really at the heart is quantum mechanics and a quantum mechanical approach to understanding a huge variety of two-body processes. Okay, so here I have a schematic of a model cloud where the x-axis is basically depth into the cloud as measured by visual extinction, optical depth in the visual range. And I'll come back to that. But interstellar chemistry in a nutshell, I'm actually surprised that we haven't seen this simple view graph before in this meeting. So it summarizes the basic two-body gas phase processes. I also have surface formation on this list, which underlie our understanding of how molecules how they're formed and destroyed in the interstellar medium. They include processes which give rise to bond formation, rate of association, grain surface formation, associative detachment, processes that give rise to bond destruction, such as photodissociation, dissociative recombination, collisional dissociation, bond rearrangement, ion molecule exchanges, charge transfer, and neutral-neutral reactions. And Alex has contributed to our understanding of all of these processes on the quantum level, then assembling them into models which then can represent these beautiful objects that we observe. I also want to mention some classic papers going back to Bates and Spitzer, Herbst and Klumper in 1973, and a beautiful review article by Dalgarno and Black in 1976, writing down basic facts basic information about these various processes. Well, how did I meet Alex? I want to talk about that just a little bit. Well, it's actually an interesting story. I was an undergraduate. I was at Harvard College, and it was my senior year. And I'd run out of, I don't remember exactly how this happened, I'd run out of undergraduate astronomy courses to take. Maybe there just weren't that many. And my good friend, Alan Porter, who was also an undergraduate astronomy student as well with me, we were sort of trying to figure out what should we do our last semester. I think it was spring semester of senior year, I'm not sure, maybe it was the fall. And we had this crazy idea to sign up for a course that we had heard about called Astronomy 236, Atomic and Molecular Processes in the Interstellar Medium. We knew nothing about what that was, and we certainly didn't have any, just knew nothing about what that was, but we had this crazy idea to go find out. It turned out that this was a graduate course, but none of the graduate students that year wanted to take the course. So actually, it was only me and Alan who showed up. Nevertheless, Alex, the teachers, Alex Dalgarno and George Victor, decided that they were going to teach this course. And we were the only two students. Now, I have to say that I distinctly remember that most of the course was way over my head. I mean, I remember understanding maybe 20, 30% of the material. But what was really crucial for me, at least, was the term paper. And here I have, this is the actual copy, I still have it, a scanned copy of my original term paper from that year. Charge transfer and sulfur ions in planetary nebula and H2 regions, my term paper. And the goal of this paper was to simply try to, at that time, Alex was doing a lot, as Tom had just mentioned, was doing a lot of work on charge transfer, and it was applying the rate coefficients that he was working out to astrophysics. And it's really sort of mind-boggling today to just think that in the 1970s, charge transfer was really not included in plasma codes. And so this was just an attempt in this term paper to actually calculate what the effect of rapid versus slow charge transfer reactions would do on the ionization structure, particularly the sulfur abundances in planetary nebula. And I was really turned on by this. I said, I'm actually doing a little, it was inspiring. Now, I have to say, I just want to say, it's sad to mention that neither George nor Alan are alive. They both have died. And so the remaining members of that particular course are Alex and me. So let me just, again, charge transfer and astrophysical plasmas, the importance, in a nutshell, two statements can be made about that. First, you can imagine a general process of charge transfer process as listed above. It's important for two reasons. One, it's a neutralization mechanism for ions Xn plus, and the product ions are very often produced in an excited state, so the charge transfer, as we've also heard at this meeting already, is also an excitation mechanism for the product ion Xn minus 1 plus. And in fact, my first paper with Alex was precisely about this excitation process. Alex, do you remember this diagram? Anyway, this was from our first paper from Dalgarno and Sternberg. You can see it there in 1982 AppJ Letters. And at that time, actually, this was already after I had graduated. I was not sure what I wanted to do with my life. But Alex very kindly hired me as a research assistant before I went off to graduate school. And actually, this was a paper published before I went off to graduate school, which turned out to be at Columbia University, as it turned out. And here on the right-hand side, you see the reason why this was so interesting, at least initially, was that charge transfer was exciting the upper state in the diagram, and then as a result of that excitation, a cascade down to the singlet S metastable state. Is there a pointer here? Does this work? I need a pointer. That doesn't work. And there was a possibility that the excitation of the singlet S state would affect the intensity of the metastable transition from singlet S to singlet D, which is a classically used probe of the electron temperature in H2 regions in planetary nebula, under the assumption that these levels are excited purely collisionally. So this was very exciting. As it turned out, the effect is very weak because one can directly determine the magnitude of the effect by the strength of the permitted 5592 line. It does work?
It does.
Oh, there it is. Now, I just want to see, this is actually a scanned-in version of the original journal. I just want to make one correction to this. It really should be letters to Alex. See, I was only vaguely aware of what it meant to be editor in those days. And it still boggles my mind, Alex, that you were editor for 29 years. It's just incomprehensible to me, but that you were doing that and everything else all at the same time. Well, we've heard a little bit about heating and cooling. Now, in this very important review article that Dick McCrae and Alex Dalgarno wrote in 1972, they did, among other things, discuss cooling of the neutral interstellar medium, and pointed out that fine structure emissions from singly ionized carbon would be a major cooling process. Neutral impact excitation followed by emission of a photon would be a major cooling process. And on the left-hand side, what you see here are diagrams taken from a famous paper by Thielens and Hallenbach, 1985, showing the efficiency of this cooling process as a function of temperature on the x-axis for various densities ranging from 10 to 10 to the 4 particles per cc. Now, at the time that Alex and Dick McCrae wrote their review, they were actually focusing on the low-density diffuse interstellar medium, and in particular on what we today know, we know that the diffuse interstellar medium, low-density diffuse neutral interstellar medium in the galaxy is multi-phased and consists of two components, a cold neutral medium and a warm neutral medium. In fact, in the theory for this two-phase structure, this particular transition dominates the cooling of the cold phase. Lyman alpha is the dominant coolant for the warm phase. That's the reason you get this multi-phase behavior. But the Dalgarno-McCrae paper was written before this 157.7 micron line was detected. Far infrared detectors did not yet exist then. But they were getting close. They were coming. And there was a big surprise because a few years later, when they were first detected, and the first detection by Russell et al. In 1980, Learjet, and then subsequently routinely from airborne and space-based spectrometers, the surprise was that the intensity of the line per particle was actually much higher than one would have expected from the diffuse medium. It was actually coming from much denser material. This was a surprise, and it basically, what it opened up was an entirely new parameter regime to study in the interstellar medium that had not been really fully explored before. Okay. Just want to mention a spectacular detection by Maialino et al. Of the C+ line recently in this high redshift quasar. I think Aviv already showed this beautiful detection. As we'll see, this line, in addition to being important as a coolant, is also a probe of star formation. So star formation rate inferred in the host galaxy of this quasar is 3,000 solar masses per year, much higher than the 5 solar masses per year in our galaxy that I mentioned. Well, Thielens and Hollenbach, this dense gas, which was also clearly exposed to dissociating and ionizing radiation, otherwise the carbon would be in CO and not in C+. This dense gas and this new parameter regime was opened up in a famous paper by Thielens and Hollenbach, and they refer to these regions as photodissociation regions, PDRs. They refer to them because they're imagining a system of stars, young stars, embedded new OB stars, which are massive, short-lived, producing a lot of ionizing and ultraviolet radiation, impacting the surrounding molecular material, photodissociating the molecules, and also giving rise to an infrared response, which one could then observe spectrally in the infrared and far infrared. So they refer to these as photodissociation regions. Now, Alex actually introduced the much better name, and I still remember the day that we were talking about this, and said, well, should be better. Better term would be photon-dominated regions, and of course, the clever thing about this is it still has the same acronym. So that was a really nice sort of little joke, but the photon-dominated regions is a better name mainly because both the formation and the destruction of molecules in these PDRs actually initiated by the radiation fields. So thank you for that name there. So dense PDRs, these are regions exposed to intense far UV fields and star-forming molecular clouds. They're important sources of luminous atomic fine structure molecular line cooling radiation and far infrared thermal dust continuum emission. And here's a typical spectrum. The interesting thing, quantitatively, one can immediately see from this, the continuum is actually due to re-radiated dust emission. The dust gets warm, is re-radiates as quasi-thermal. The line to continuum ratio observed is typically 0.1 to 1%. And this is readily understood as a product of the primary heating mechanism. The fact that it's photoelectric heating is crucial. And it's actually, I won't really go through all of this, but it's listed there. You can very easily work out that the expected heating efficiency for this process is of order a few percent, which is actually consistent with what's observed. So we really understand that. Now, I want to just briefly sort of show you the schematic diagram of what the chemical structure, and this goes back to the kinds of models that Alex developed with John Black already in the 1970s. Basically, a steady-state model is input radiation on one side with visual depth into the cloud is measured by visual extinction. As the radiation is absorbed, there's a conversion from atomic hydrogen to molecular hydrogen, deeper in a conversion from C+ to carbon to CO, and then as one considers elements that are less and less abundant, the conversion occurs deeper and deeper in. And the structure of these clouds theoretically have been pretty well understood by now. A lot of work has gone into understanding how the chemical properties depend on all of the astrophysical parameters. And all of these parameters enter into the global star formation rate that occurs, controlled to a large extent by the ionization structure, which controls the collapse times, especially if the collapse is magnetically regulated. Now here's a typical diagram showing the carbon-oxygen chemical network involved, that's included in the kind of modeling to reproduce that structure. So this is a diagram from a paper that Alex and I published in the mid-90s. Well, let me jump to a related subject right away, to molecular hydrogen, which I wanted to say a few things about molecular hydrogen, which has been a major focus of Alex's work. And here are some, molecular hydrogen is widely, of course, is the most abundant, goes without saying, the most abundant molecule in the universe, and although it's generally impossible to observe directly, because when it's cold and quiescent, it's not possible to observe it. But it is, nevertheless, in many situations, is observable, and it's been observed in planets and protostellar jets and planetary nebulae, which are the blown-off atmospheres of evolved stars, and in shocked regions and star-forming regions and external galaxies. So here's just a run of examples. And all these observations are, as was shown in that previous slide, are all imaged in the 2.12 micron transition of molecular hydrogen, vibrational transition from 1 to 0, and which is a quadrupole transition. The idea that molecular hydrogen might be observable via quadrupole transitions goes back to Hertzberg, a beautiful theoretical paper from 1938. I believe it was then, many years before it was finally detected in planets. I think it was Spinrad who detected first in planets. Now, Alex did a huge amount of work, step by step, in a very characteristic way, step at a time, perseverance, confidence, to build up the necessary basic molecular data to understand excitation of molecular hydrogen via radiation. And it involves absorption from the ground state to two excited states, so-called B and C states, followed by radiative decays and allow transitions to the ground state or into the continuum of the ground state, followed by decay. So this is a way of producing the emission that one sees in the near infrared via absorption of far ultraviolet 10 eV, typically photons in transitions from the ground electronic state to the excited electronic state. And these papers have been mentioned before, and I'm putting them up again. There's Allison Dalgarno for the oscillator strength for the Lyman and Werner system, Stephens and Dalgarno for the spontaneous radiative transition probabilities, and more recent work I want to mention by Abgral and Weff on this. And then for the quadrupole transitions, two papers, Turner et al. From the 1970s, yet again it's more accurate, although it's so accurate that it's almost too accurate. We don't need this accurate, but there it is. I want to mention this beautiful, I remember as a student this making an incredible impression on me. This still makes an incredible impression on me. I think Aviv showed this. You see, one of these, what Aviv did not say when she showed this is that one of these figures, there's two parts, there's an upper part and a lower part to this figure. One is theory, the other is experiment. Now, which is which? I don't know if you can tell which is which. Which is the theory here and which is the experiment? I mean, the match is so incredibly good. So I'll just tell you the answer, so experiment theory. And let me just read the abstract, part of the abstract. This emission, it corresponds to the transitions from the various vibrational levels of the B sigma state into the continuum of the X sigma G state. The fluctuations arise because of the effect of the non-terminal maxima of the continuum wave functions and represent the first clear-cut example of Condon's diffraction bands predicted in 1928. So here's a paper that was published in 1970. So let's do the math. So decades later, finally the explanation. So again, time span. Well, all of this was then put together by John Black and Alex in John's thesis, part of John's thesis, which was really an incredible thesis, in a calculation of the expected infrared molecular hydrogen spectrum that will arise as the photons simply cascade through all of the vibrational levels in response to excitation by a radiation field. And there's their spectrum, published in 1977. This was long before this was ever observed. Right? It was only observed, this was actually finally observed 10 years later. Actually, it's sort of funny. If you look up NGC, I just noticed this the other day, if you look up NGC 2023 on Wikipedia, it'll say, the brightest source of fluorescent H2 emission known. That's what it says, but what do you learn from, where did that come from? No. So getting back to, this is really the context of these observations of the C+ line were really the motivation for my PhD thesis, looking at what happens in denser gas. And this is one of the papers primary paper from my PhD thesis. where we, at that time, by the time it appeared, I was already at Tel Aviv University, and actually I put up my life path. Cambridge, New York, Columbia University, back to Cambridge, Tel Aviv, Munich, Tel Aviv. So it's 30 years in one line. Thanks very much. What we did in this paper was simply to study in detail the thermal properties of the Pdrs and the detailed molecular hydrogen spectrum from the low-density regime to the high-density regime. And what was interesting, what we found was the not too surprising result that as one goes to high densities, the emission thermalizes. But this was important because up to that time, a thermal spectrum like you see on the right was considered to be a clear diagnostic of the molecular hydrogen emission spectrum that you get in a shock wave, where here we were producing it in a completely different way. Now, we heard about these collision processes this morning, and there's still a great need in these kinds of models for accurate rate coefficients for these processes. Let me turn to some more recent observations. This is a picture of two galaxies which are colliding, the antenna pair. This is an image from Hubble Space Telescope. You see a huge number of superstar clusters, young star-forming regions. This is an image at longer wavelengths from the Spitzer telescope, so it's less resolution, lower resolution, longer wavelengths. Most of the energy is coming from embedded regions. One can do long-slit spectroscopy here. Here's a beautiful spectrum by Gilbert et al. From the Keck 10-meter telescope, ground-based. And in there are all these beautiful H2 vibrational emission lines. This is the black and Dalgarno spectrum in a starburst galaxy. This is my favorite example of this. It's absolutely great. There it is. Okay, I want to continue on to a related but different subject, molecules in the C4II galaxy NGC 1068. I mentioned at the start that galaxies have black holes. Something has gotten caught in my throat. I don't know what it is. And in our own galaxy, this black hole is, this monster lurking at the center is quiescent. It's not doing anything. But sometimes these black holes start to accrete material. And when they do, the gravitational energy released is enormous. And a lot of that comes out as radiation, which then affects the surrounding medium. You can also see this radiation directly. So NGC 1068 is a famous example of a relatively nearby galaxy where this is occurring. Distance is only 50 million light years. The black hole is producing an accretion luminosity of 2 times 10 to the 11 solar luminosities, and a lot of this comes out in the X-rays. Now, amazingly enough, one can also, so I think this is 20,000 light years across. Zooming in the millimeter waves, one sees a variety of molecular species from the molecular gas, and you can see there are two parts. There's an outer ringish or spiral arm kind of looking thing, and then an inner nucleus. So we have CO, HCN, 12 and 13 CO, and CS. Let me focus on the CO, carbon monoxide. So there's the image in CO, but when one looks at it in HCN, what one sees is only the nucleus. Now, part of this effect, part of the reason the HCN is strong in the nucleus and weak in the arms is probably a density due to the fact that HCN is a good tracer of dense gas, and the gas density in the nucleus may be high, but it's such a large effect that it may be chemical. And in fact, Steve Lepp and Alex had the idea that this might be due to the fact that there's enhanced HCN production due to a high ionization rate due to X-ray penetration. Beautiful idea in this paper. This gives rise to the whole topic of so-called XDRs. These are molecular regions which are exposed instead of to far ultraviolet radiation to X-rays. X-rays are much more penetrating than the ultraviolet radiation which is absorbed by dust. And here's a schematic diagram of what what an XDR is like. And I want to mention Minyan's PhD thesis, which studied in detail the thermal and chemical structure of such XDRs. Critical parameter is the ratio of the X-ray energy deposition rate to the gas density. I'd like to mention another piece of important work that Alex has done relevant to the XDRs, and that's the way in which the fast electrons, which actually do the work, lose their energy, and it's basically Coulomb scattering, excitation, and ionization. An interesting thing about the ionization process is that when you do produce this electron via ionization, it immediately gives rise, this energy actually is immediately thermalized due to these chemical reactions. Another thing that worked out in this very nice paper by Alex is the energy loss per ion pair, which turns out to be 37.7 eV. So that means that the heating efficiency is 15.4 over 37.7, which is 0.4, which is much higher than PDRs I mentioned, is a few percent. This is a very basic physical difference between. So here's a calculation that I did recently with my student Guy Bourguer on what the chemical structure of a ion molecule-driven molecular cloud would look like, a la basically the calculation that Steve Lepp and Alex did, is more updated. There's one parameter in the problem, that's the density over the ionization rate. And here's a calculation of that. And a high ionization rate, as you can see in this diagram, gives rise to, in fact, a high HCN to CO ratio, as Steve and Alex pointed out in their paper. It also predicts a high CN to HCN ratio, which is also beautifully consistent with more recent observations by Usero et al. So it is compelling that the molecular gas in the center of NGC 1068 is due to X-ray ionization. Let me just give me just a few more minutes before you stand up. I see you. I see you there. Let me just show these. I want to show the highest resolution imaging of highest resolution data that we now have on molecular gas in NGC 1068 or actually any active nucleus, and this comes from adaptive optics imaging, which enables diffraction-limited observations from the ground. In other words, it's as though there were no atmosphere. So the images produced are actually better than what's produced by the Hubble Space Telescope. And what's interesting is this diagram. So the spatial resolution is about 0.1 arc seconds. And this is a zoom in on the innermost region. And what one sees clearly, again in this molecular hydrogen emission line, are streaming motions directly into the black hole. We estimate that its streaming motion is around 15 solar masses per year, but I must say this is highly uncertain because we have no idea what the excitation mechanism, we don't know how to convert a line intensity into a gas mass very accurately. So we still need to figure out what the excitation mechanism is in this source. Well, let me conclude with one more topic. I'll do this very quickly. Very quickly.
We may be ahead a little bit because Cesare has not showed up yet.
Right. So I have a little time. Also, I have to catch an airplane, so I know I'm stressed.
So you're pushed in both directions.
Very good. I'm good. So I'm just about done. Let me just give me 5 more. So here's this is you'll like this, Pat. This next slide. Okay. So this is I showed this diagram before, and there's a prediction here that the molecular clouds are primarily CO. I put prediction I put prediction in quotation marks because it was known long before the theory. So this gives rise to the basis of using CO as a proxy for H2. And so here's Pat's beautiful map of the Milky Way or of an external galaxy. So I just want to in 2 seconds, flash up some recent work that Alex and I have been sort of doing on and off for the last couple of years. And I think we're now in a fairly advanced stage here. And that's the question of what were the first molecular clouds like? When I say the first molecular clouds, I mean molecular clouds that formed after the first generation of stars. The first metals were produced in the universe. There was a very early phase, perhaps very brief, where the metallicity the heavy element abundance was far lower than what it is today. And it turns out that if you actually just used basic theory, ion molecule theory, to simply ask the question, what does the structure of a shielded molecular cloud look like as a function of the metallicity, you get this interesting result that as one reduces the metallicity, the OH abundance eventually exceeds the CO abundance. And it's really quite simple. This must it's simple to understand why this must happen. And there's a very simple diagram showing that the CO is actually formed. It's a very simplified version. CO is formed in reactions of OH with C+. And so the ratio of CO to OH will clearly work out to be proportional to the metallicity up to some factors. Now this calculation does not include radiation. You can far UV radiation. It only includes, it's an ionization-driven ionization, but does not include photodissociation. If you put photodissociation in, and I'll skip what this means, you reduce the abundances of these molecules, but you don't affect the critical metallicity, which turns out to be of significance around 10 to the minus 3, at which the clouds become OH dominated as opposed to CO dominated. Of course, if photodissociation is important, then the molecular abundances are suppressed and most of the cloud is atomic. So we're in a golden age. I'm finishing now. We're in a golden age. And so much of this golden age has been led by Alex. So again, we're all so incredibly grateful in so many ways. And I want to finish with this picture that Evine already showed. So I'll show it again. And Alex, regards. Thank you.
We can spend a few minutes for questions if we have some.
Yes.
You mentioned the average density of one hydrogen atom per cubic centimeter in the galaxy. This goes back to Eddington's 1926 Bakerian lecture. Now, so much has changed in our knowledge of the structure of the galaxy. Why is that number not changed?
That's a good question. It was a good guess, so I don't know how we got that number. But I do think it is still one, not too far from one.
I mean, this still comes back from that number.
I've never thought of that. But, do you know how he came up with that number?
I read the paper, but I don't want to be tested like most students. It was a cultural question, really.
I just don't.
Well, it's an interesting question. Where does the fact that oxygen is more abundant by carbon in the stellar medium, for example, by a factor of a few, where does that come from? Most people don't realize how far back it goes. It goes back to Russell. It came from analysis of the spectra of cool stars. It is now essentially confirmed by recombination lines and things. But it's very interesting that if you assume that carbon is greater than oxygen, by just a factor of 2, you get some rather prodigious and interesting changes.
Mm-hmm. No, absolutely. Yeah, Alyssa. Which at redshift, we're talking, this would be, first of all, it's not even clear what redshift we're talking, around redshift 10.
Yeah.
So I don't know. Yeah.
One last question.
There's a question here.
Yes.
Amiel, a question about the XDRs in the galactic nuclei. One thing we found in our models of the young stellar objects is if you have ices evaporating, like in a hot core region, and you bring water from the grains back into the gas phase, it changes your XDR chemistry and your XDR structure, and certainly it affects also the HCN over CO ratio. Have you ever considered that for sort of the galactic nuclei, whether that could play a role?
No. So what I showed you there was a purely gas phase. And it's actually worse than what you're saying because, in fact, for example, that's, even in the gas phase, there are various ways of producing for example, a high CN over HCN. You can get this in Pdrs as well. So this is actually just restricted to the gas phase without worrying about evaporation. It's still not clear how from simple gas phase chemistry one would actually distinguish between clouds which are exposed to starlight versus X-ray accreting black hole. So the answer to your question, is that no, I have not considered that.
Right.
But it's important to consider it.
Yeah, I think it must be very high density gas, which at some stage must have gone through a cold phase. So it must have accreted ices, which are now evaporating. So it would be interesting to see if we can find some test of that.
Is Marco done? Is Marco Spans?
No, they are also not including the ices. This is mostly the work by Pascal Stauber in Zurich. Yeah.
So, great.